and then start sharing my screen. And okay. Okay. So GN 200, and today is February 8th, 2021, and today simply we'll continue with the discrete random variables families or distributions. And in particular, we will do geometric and Poisson distribution. And we have one announcement, which is computer assignment. Computer assignment 1 is posted. And it's due end of next week. Also, you received to do that homework 1 is extended till end of this week. Okay. So let's start with today's lecture. So last time, to link this lecture to last lecture, last time we did 2 distributions. We did uniform distribution, and as mentioned, it's used to model random experiments where outcomes are equally likely. So any experiment in which we have outcomes that are equally likely, they have the same probability, then we use the uniform distribution. The second distribution that we talked about last time is the binomial distribution. And the binomial distribution is simply repeating Bernoulli trials n times and counting the number of successes x out of n, and the probability of success in each trial is p. And we mentioned last time that the distribution for the binomial is n choose x, p to the x, 1 minus p to the n minus x, and x can be any number between 0 all the way to n. So I have, so here, important to note here, number of trials is fixed. number of successes is random. That's why we calculate the probability of X. We do not calculate the probability of something that is fixed. I cannot tell you, like the example of last time, we are transmitting 4 bits. What's the probability of transmitting 4 bits? I'm telling you that we are transmitting 4 bits. So it's not a random thing to calculate the probability. I can ask you, what's the probability that I will get 1 bit in error or 2 bits in error, or so on and so on. Let's do one last example on binomial before we move to today's distributions. So assume that I give you an exam with MCQ questions. So MCQ exam. MCQ, of course, you know, it's a multiple choice questions. An MCU exam with 30 questions. Where each question has 4 answers. And let's assume that one of you just does not understand anything in the course and just guesses answers for each question by guess. So you have a set of 30 questions, and you have for each question you have 4 answers, and then there is a student who guesses. He does not have any idea about what is going on. Real life experiment. Okay, good for you. It happened for me. It does not mean that you are a bad student if you do this. I remember when I did the GRE exam. GRE exam is an exam that you take if you want to do PhD or graduate studies in general. And there's part, of course, you don't take the whole exam. There's an English part for the GRE that's so difficult. Even those who are native, whose language is, whose English is native, they don't know the idea. They ask about really hard things. So I remember that exam, I had to guess most of the questions. I had 1 or 2 questions that I knew the answers. What is good is that universities, they know this, and they don't care about the English part of GRE at that time. They just take the analytical and quantitative part, which has to do with your math and quantitative skills in general. Okay. Fine. I can ask this question first. What is the probability that the student answers more than 20 questions correctly? So what's the probability that the student answers more than 20 questions correctly? So we know that what's n in this case? What's the number of trials? So the student is taking the whole test. So the number of trials is 30. Right. 30. And I am interested in probability of X greater than
or equal to 20.
No, greater, not equal. Actually, in the morning I put it as greater than or equal, but the way I'm phrasing the question, I said at least 20 questions correctly, then greater than or equal. If I say answers more than 20 questions correctly, then 21, 22, 23.
Okay.
What's P? What's small p? What's the success probability of each trial?
1/4.
1/4, right? So here we want probability of x greater than 20, which is probability of x equals 21 plus probability of x equals 22, all the way probability of x equals 30. And you can write this as sum x equals 21 to 30, and then you have 30 choose x, p, which is 1/4 to the power x, and 1 minus 1/4 to the power 30 minus x. And if you calculate this carefully, you'll find that this is very low probability. Very low probability that if you had to guess all the questions, then the probability that you'll get 20 or more than 20 questions correctly is very low. Okay. Right. I can also ask, what is the probability of answering all questions correctly? You can do this even without using the binomial distribution. So I'm really asking what the probability that x equals 30. You can, of course, use the rule. So probability that you will answer all questions correctly, it means that it's the probability that you will answer the first one correctly, and the second one correctly, and the third one correctly.
to the power 30.
So which is 1/4 to the power 30, which is very small number. Very small number. You know that if you multiply a number less than 1 by itself many times, it gets smaller and smaller. But also you can do this using the rule. So probability of x equals 30 is n choose k, so 30 choose 30, 1/4 to the 30, 1 minus 1/4 to the 30 minus 30, and for sure you know that this is 1, so it's power 0, this is 1, and also this is 1. Why? Because this is simply 30 factorial over 30 factorial times 30 minus 30 factorial, and we know that 0 factorial is, we know this. So probability that you will answer all questions correctly is very, very, very small. What's the chance that you will answer all of them wrong? If I ask them, just probability of all
By 4.
questions answered wrongly.
Doctor, can we say 1 minus the above answer?
No. 1 minus 1 is 1 minus this. What will it will give you? What? The complement of all correct is the event that at least 1 is wrong. So it means 1 is wrong, or 2 is wrong, or 3 are wrong, or 4 are wrong, or 5. So it will count all other scenarios. But here I'm asking probability of all questions answered wrongly. So probability of x equals 0. So this means that the first one is correct, and the second one is correct, and the third one is correct, all the way the 30th is correct, right? So it's 3 over 4 to the power. From the rule, you can do it also from the rule, probability of x equals 0, which means 30. Choose 0, 1 over 4 to the 0, 1 minus 1 over 4 to the 30 minus 0. Again, this is, oh, sorry. This is 1, and this is 1. Why? Because this is 30 factorial over 0 factorial times 30 minus 0 factorial. And this is, of course, 3 over 4 to the 30. So, bottom line, in binomial, always remember this. Number of tries is random. Number of tries is fixed, sorry. While number of successes is random. So if you repeat this experiment, if you take the exam multiple times in one occasion, it might be one problem is wrong, other occasion 2, 3. So the number of correct answers that you get is random. Which leads us to the next distribution that we want to talk about, which is the geometric distribution. Which is not exactly the opposite of binomial. The opposite of binomial, there is a distribution that we will not cover if you want to look at it, which is the, we call it negative binomial. And geometric is a special case of the negative binomial distribution. In the past, by the way, probability course in the past used to cover more material, but we realized over the years that, and when I taught this like 10 years ago, we used to cover 2 other distributions, the negative binomial and the hypergeometric. We are not doing this now because it's kind of heavy, and I think what we are covering will give you enough idea for you to be able to deal with other distributions that might come across you in the future. Type geometric distribution. What is it exactly? We are talking about Bernoulli trials again. Repeating a certain try that can be a success or a failure. So, geometric distribution encounters repeating a Bernoulli trial until we get a success, and then we stop. So basically, with geometric distribution, if we go back to our example, so I can design the exam in a certain way. So I will let the students take the exam. Once you get a wrong answer, you stop. Or once you get a right answer, I can make the exam freeze. So you go, you keep answering. If it's wrong, it gives you another question. If it's wrong, it gives you a third question. You only stop once you have a right answer. Okay? So you repeat the problem until you get a success. Also, I can tell you, go and flip a coin until you get a head. So one of you comes back to me and said, okay, on my first try, I got a head, so I stopped. Another person might need 5 tries until he gets a head. Probably a third one will go and never comes back because he keeps flipping it. He gets tail, 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 tail. In theory, this might go to infinity, right? Very low probability, very, very low probability. But according to what we mentioned, remember last time, Murphy's Law? Murphy's Law tells you that the very low probability events will happen. might happen now, it could have happened 100 years ago or after 100 years, so it's very low probability events happen. Okay. So in geometric distribution, number of trials, is it fixed or random? The times that we repeat the experiment, is it fixed here or is random?
It's random.
It's random, right? Because we don't know in advance how many times I need to repeat the experiment to get the success, because success is a random thing in each trial. So number of trials is random, while number of successes is fixed, which is 1. I'm telling you, stop at 1. So I'm not looking for, I cannot calculate the probability of success, because I'm telling you by design, the experiment that we are interested in is to repeat the experiment until you get a success, and then you stop. So if you think distribution, you find out that it consists of x minus 1 failures followed by a success. So to do the experiment, you answer a question, though it's wrong, you answer it's failure, failure. And then once you have success, you stop. So let's assume this is x minus 1, and then this is one success. And these are the failures. Which means that I can simply write my f of x as a failure, which is 1 minus p, times another failure, times another failure, and then a success where I stop. So I have x minus 1 tries of failure and then followed by a success. So simply f of x is 1 minus p. Let me write it. So f of x is 1 minus p to the x minus 1 followed by a success. So what's the range of x? Anyone? X, again, this is the number of trials.
From 1 to infinity.
So at least x cannot be 0. Remember, in the binomial, x can be 0 because x in the binomial reflects the number of successes. And in principle, you can have 0 successes, right? But here, x is the number of trials. So at least you need 1 trial to get a success, or 2 trials, or 3 trials, all the way to infinity. Let's do an example so that things are clearer. Sorry. What's wrong? Example. In a computer network, I just came up with this example in the morning. In a computer network, buckets, we send information in buckets between nodes, between routers, so that when you send an email, your email, or even when I'm streaming this lecture, the video is splitted into packets, and these packets reaches the home of each one of you through points in between, right? Through routers. So in a computer networks, we send information between nodes or routers in buckets. And every time we send a packet, we wait for what we call acknowledgement, so that if there is an error, the bucket is sent again. طيب, assume that packets arrive successfully with probability 0.95, and I can ask I can ask the following question. So what is the probability that a certain bucket needs to be sent 5 times for it to be received successfully? So I'm sending this bucket. Every time I send a bucket, I wait for an acknowledgement from the receiver. If the acknowledgement tells me it's good, then I will move to the second bucket and send it. If it's good, move to the third bucket. However, if the acknowledgement tells me there was an error, I will send the bucket again and wait again for acknowledgement. If there's an error, I will send for 3 times or 4 times or 5 times. Of course, we will not do this forever. Usually, networks, they have certain amount of time they wait for those buckets to be delivered. If they are not delivered within a certain time, we just discard it and move to the second packet. So here we know that P is 0.95, and I'm asking what's the probability that X equals 5. So I need 5 times to deliver the bucket, which means that I have failure, 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 and then success. Or I can just use the PDF here, which is 1 minus 0.95 to the 4, followed by 0.95, which is a success. I also can ask, what is the chance that we need at most 2 transmissions to have successful arrival? At most 2 means what?
Probability of S less than or equal to.
Yes, so probability of X less than or equal to 2, which is probability of X equals 1 plus probability of X equals 2. Probability of X equals 1 means you have success from the first try, so it's simply 0.95. Probability of X equals 2, you have a failure followed by a success. So the geometric distribution, again, is the scenario where when you keep sending or keep repeating the experiment until you get a success. What's the mean and variance of geometric distribution? Very simply, mean and variance. Again, all of those equations, you will have the chance to have them in the exam. You know that mu, which is expected value of x, is just given by 1 over p as expected. So if you have the chances, the probability that to get ahead is 50%, 0.5, then on average you need two flips, 1 over 0.5, which is 2, to get ahead, right? And the variance, which is variance of x, is simply given as 1 minus p over b squared. And again, you can prove those two formulas going back to the definition of the mean and the variance of random distribution and writing it, you can prove it. Okay. But before we leave the geometric distribution, we have to talk about one important property of geometric distribution. One important property of geometric distribution is what we call lack of memory. So geometric is the only discrete distribution that is memoryless. What does this mean? As we will see also later on when we talk about continuous distribution, we'll find out that there's only one continuous distribution, which is the exponential, that is memoryless. So what does memoryless mean? So assume that I ask one of you to go and throw a dice, okay, and keep throwing the dice until you get number 1, and then stop. So what's the probability of success in each trial for this experiment? Someone is saying did not understand. We'll come back to point 2. I'm not sure what point 2 you are talking about, but we can come back to it. Let me finish this. At the end, we can come back to it. So 1 over 6, right? If I ask one of you to go and throw the dice to throw a dice until you get number 1. So in this case, probability of success for each trial is 1 over 6, right? Right. So you went to the so before you start, I can ask you, what's the probability that you will need you will get 1 in the 5th try? Let me write this down. So assume another example. Throwing a dice until you get 1. So this is geometric with P equals 1 over 6. So on average, we expect that you will need to throw the dice 6 times, 1 over 6, to get the number 1. Right. So before you go, I will ask you, what's the probability that x equals 5? That on the 5th trial, you will get 1. So you tell me, okay, this is 1 minus p to the 4 times p, according to the PDF that we've just talked about. So it's 1 minus p to the x minus 1 times p. So p is 1 over 6, 1 minus p to the 5 minus 1. So this is, let me say 5 minus 1, just to make it clear. 5 minus 1 So again, this is 5/6 to the 4 times 1/6. طيب. So this is before you start. This is the probability that you will get the number 1 in the 5th try. طيب. You went to the side of the room, and someone wrote 1/6 to the power 5. 1/6 to the power 5 means that you will get 1 in 5 trials in sequence. So you'll get 1 in the first trial, and the second trial, and the third trial. Anyhow, let's go back to our example. So you went to the side of the room. You started throwing the dice. First one, you did not get 1. Second one, you did not get 1. Then I went to you, and I asked you, how are you doing? And you said, I already did 2 trials, and I did not get 1. Okay? So you did already 2 trials, and you did not get 1. So now I will ask you, what's the probability that you will get 1 in 3 trials? After 3 trials, from that point of time. So you already did 2, and now I'm asking you, what's the probability that you will get 1 in the 3rd trial? Is it the same probability that you will get 1 in the 5th trial from the beginning? So assume, let me write this down. Think about it. Assume you did 2 trials already without getting 1. Now, at this point of time, what is the probability of getting 1 in the 3rd trial from that point of time? The memoryless property tells you, if you stop in the middle and you start calculating probabilities again, forget about the past. Forget about how many trials you did and start all over again. So if I come to you after the 2nd trial and I ask you, what is the probability that you will get 1 in the 3rd trial? It's like I'm asking you, what's the probability of x equals 3? And you just do it 1 minus 1/6 to the 2 times 1/6. So just forget about past, which means that this is the meaning of memoryless. You don't care about what happened in the past. You start fresh. So if we are if this is the timeline, for example, and this is 0, we were standing here and looking where at 5. Let's say at 5, we are looking at 5. We calculated that we need 5 trials to get 1, and then at 2 I came to you and to check on you, and now I asked, what's the probability that we'll get a 1 after 3 trials? Then this is given by probability of x equals 3. It has nothing to do with when did you start your experiment. So it is memoryless, and that's why we formally say that probability of x equals t1 plus t2 . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . given that x is greater than t1, this is simply probability of x equals t2. So in the above example, t1 plus t2, t1 is 2, t1 plus t2 is 5, so t2 is 3. So regardless of how many trials you have done, inshallah, you did 100 trials, I came to you and I asked you, what's the probability that the next trial you'll get ahead or you'll get 1? It's 1 over 6. What's the probability that in 3 trials you will get 1? It is this probability, regardless of how many trials you did before. So this property is the memoryless property, which is a unique property for the geometric distribution, and it's, as we said, it's a property also for the exponential distribution. When we come to the exponential distribution, we can prove this using, for sure, you can use this using the conditional probability rule that we talked about in the previous chapter. Let's take attendance now. Please go to your Blackboard. I will enable the attendance very shortly. No factorial. Sorry, no factorial. This is no factorial. This is surprisingly. Just say this is surprisingly. This is no factorial. Okay. Please check in your attendance in Blackboard. MashaAllah, someone has just signed in. It seems that you tell each other when I'm taking the attendance, so that people will come in and check their attendance. So MashaAllah, two people. Yes, someone is asking about the quiz. The quiz that I haven't started the grading yet. Sorry. I will hopefully tomorrow we have the break, the sports day. So probably I will start grading, inshallah. Muhammad, go ahead. You want to ask question?
Doctor?
Yes.
Could you please tell us about the assignment? What is it about?
Which assignment?
The computer assignment. There was a discussion that you have to go to city center. I'm not sure. That's why I'm telling you. Just if you can give us a brief explanation about the assignment.
Okay, let me do it at the end. I want to finish Poisson, and then we'll do it at the end for those who want extra explanation. Yes. Okay.
جزاك
Yeah. طيب. The final discrete distribution that we are interested to talk about is the Poisson distribution. Poisson distribution is not like the previous ones that you have very exact scenarios where you can apply it, but rather it comes with experience, and that's why يعني, probably 99% of the times when I ask about Poisson in an exam or in a quiz, I tell you that this follows a Poisson distribution. So let's write a little bit about Poisson. So the Poisson distribution describes the number of times an event occurs during a specified interval. And this interval, which can be time, distance, area, or even volume. The occurrence of events assume we have some assumptions for the Poisson. The first one is the probability is proportional to the length of the interval the intervals are independent. I know this sounds very abstract, but you'll see that it's not that difficult. The intervals can be shortened until the probability of having more than one event is 0. So what all of this? I'm saying we sometimes face some random phenomena that can be described by a distribution called Poisson distribution. And to have an accurate description by Poisson, some formulation assumptions need to be satisfied, which I listed as 3 assumptions. Let's take some examples and see why they are Poisson distribution. So very common random phenomena. If you go very often to the bank or even an ATM machine, the number of customers in bank queue or ATM queue. Every time you go to the bank, you get a number and you see 2 customers are waiting, 3 customers are waiting, 4 customers are waiting. This number is random, and it's modeled by Poisson distribution. Also, number of dust particles on a surface. So if you have a disk in your room, and then the number of dust particles in each centimeter square on your desk is not the same. Of course, we are assuming like a disk that is away from windows, and so I know if you have just under the window, the part next to the window will have higher number of dust, but even with that, you will not have exactly the same number of dust particles on each 1 centimeter squares. The number of trees in a certain area of a jungle. And let me say wild jungle, because those farms that are planted by a human being, usually they do them in an organized fashion. But if you go to a wild jungle in which trees grow up naturally, you see that there is no specific distribution of jungles. So if you 1 kilometers of the jungle in one area will have certain number of trees, while 1 kilometer square of the same jungle in a different area will have different number of trees. Also, with Boson, the more examples we talk about, the more it's clear in your head. Number of phone calls to a customer service number, So the number of people who call like 180 or 999 or any customer service number in 1 hour is different, right? From 1 hour to the other. Finally, probably number of cars in a public car park also follows. You don't find the same number of cars in the parking lot that you go to very often. So how are these conditions applied? For example, let's take the trees in the jungle. We see that the probability of the number of trees proportional to the length of the interval. So you take a wider area in the jungle, you will have larger number of trees. You have smaller area, you have smaller number of trees. The number of phone calls to a customer service. If we talk about number of phone calls in 1 hour, you have larger number, probably double, as we'll see, on average, double the number if we are talking about half an hour. In 2 hours, usually you'll have, on average, double that in 1 hour. Intervals are independent. Yes, like on your desk, having like 10 dust particles in one area is independent of having the area next to it having 20 or 30. The number of particles in each area is independent. And in all cases, you can areas or like on your desk, you can go to a smaller area, like 1 millimeter by 1 millimeter, 1 micrometer by 1 micrometer. You can go so small until you reach an area in which you can have either one particle or none. So you can divide your surface to smaller areas where you can have either one particle or not. Even with time, you can go short in time until you can have either one phone call or no phone calls whatsoever in like each second. You cannot have 2 phone calls in the same second, and so on. So all of these characteristics help us in defining that the random phenomena that we are dealing with is Poisson or not Poisson distribution. Very common example from my field is even though it's not very good approximation but it's very common to assume that the distribution of base stations in a certain city follows Poisson distribution. In base stations, we know that there is some planning and they put them in an organized way, but unfortunately, since base stations are not planned when cities are planned, so you have the city is full of houses and service facilities, and that's why sometimes the network operators, they go to houses and they rent areas inside houses to put their base stations. So this is very common example of using Poisson distribution. So what's the distribution itself? F of x of Poisson distribution, like any other distribution, it has a certain distribution. It's given by e to the minus lambda, lambda to the x over x factorial, where x can be 0 and 1 or 2 or 3. So you can have 0 events, you can have 1 event, you can have 2 events in a certain number of, in a certain period of time, where lambda, lambda is the average, is a parameter that is given, describing the average number of events in a certain interval. So again, I want to emphasize that Poisson is a distribution that we use analogy a lot. So that's why I gave many examples to give you an idea about the randomness of Poisson distribution. What's nice about Poisson is that its mean is lambda and its variance is also lambda. Right. Let's do an example and see how to use Poisson distribution, how to use those formulas to solve for Poisson distribution. So number of calls, of phone calls arriving, let's say to Ooredoo. I always give the example of Ooredoo because I dealt with Ooredoo a lot. I've been with Ooredoo since I started using cell phones, so that's why. Not saying they are better or worse than Vodafone, but I know for sure that Vodafone has improved a lot over the years. So number of phone calls arriving at Ooredoo customer service line is modeled by Poisson distribution with an average of, let's say, 100 calls per hour. Okay, so I'm telling you that lambda is 100 calls per hour. Right. Let's start asking some questions. What is the probability that there is exactly 80 calls in 1 hour period? I'm telling you, on average, they receive 100 calls per hour. Receiving 100 calls per hour does not mean that each hour they will receive 100 calls. since this is a random process, in 1 hour they might receive 90 calls, in some hours they might receive 0 calls, in some other hours they might receive 200 calls. So this is the randomness. So I'm asking here, in a certain hour, what's the probability that they will get exactly 80 calls? So very simply, I'm asking about probability of x equals 80. According to the rule, this is f of 80, which is e to the minus lambda, so e to the minus 100, lambda to the x, 100 to the power 80 over x factorial, so 80 factorial. So of course, if I give you this question in the exam, you can leave the answer like this, because most probably your calculator will not be able to calculate this probability. I can ask also, let me ask another question. What is the probability of receiving 0 calls in 1 hour? So probability of x equals 0 is what? E to the minus lambda, lambda to the x, lambda to the 0 over 0 factorial, so it means e to the minus 100, which is a very, very small number. If on average you are receiving 100 calls per hour, the chances that you will have 0 calls, 0. You will always have calls. And you can do all questions, but what's important, let me put a note and then we'll continue with the question. Note, very important note. For Poisson, you might need to modify, not change, let me say modify. You might need to modify lambda if you are asked about a different time interval. A different interval, let's say in general, not time necessarily, different interval. شو يعني? Let's continue with our example and see what does that mean. I can ask you, what is the probability that you get exactly 30 calls in half-hour period? So if you notice, all the previous parts, I was asked about 1 hour period, right?
Now we need to know the average of half-an-hour calls, right?
Yeah. So now I'm asking about half-an-hour period. So here you need to modify your lambda. So we know lambda, that's as given. Lambda is 100 calls per 1 hour, which means the lambda new that you should use is, if I'm talking about a period of half an hour, what will be my new lambda?
Doctor, you can just half it just like that, or like there's a special way of?
No, just if I said like quarter of an hour, it's 25. 2 hours is 200 calls per 2 hours. I will do some other examples. Just scale it according to the interval. And this is one of the assumptions, is that of Poisson, which is the probability is proportional. Assumption number 1. Probability is proportional to the length of the interval. That's why we can modify the average according to the length of the interval we are interested in. So in this case, my new lambda is 50, and I'm asking about probability of x equals 30. So now x equals 50, lambda to the x, 50 to the 30 over 30 factorial. طيب. How about if I ask, what is the probability of having at most 2 calls in 1 minute period? So again, I modified the time interval. Sorry. What's the probability of having at most 2 calls in 1 minute period? So again, original lambda was, lambda is 100 calls per hour. So how many calls in 1 minute?
1.6 or 5/3.
It's 100 over 100. How many minutes I have in the hour?
60.
60, right? So, right, which is 10 over 6, which is 5/3 calls per 1 minute. So probability at most.
Doctor?
Yes.
Sorry to cut you, but the calls can be even as fractions.
If you remember, we said always the average. Lambda is the average, and the average can always be fraction, even in experiments where you have absolute numbers.
From the previous lecture, yeah.
What?
Yes, you mentioned this in the previous lecture also. Sorry.
Yeah. No, that's fine. That's fine. So probability of at most 2 calls. So x is less than or equal to 2, right? Which means that this is probability of x equals 0 calls, plus probability of x equals 1, plus probability of x equals 2. And for each one, as we do it, we use e to the minus lambda to the x over x factorial, plus e to the minus lambda to the 1 over 1 factorial, plus e to the minus lambda to the 2 over 2 factorial, which is simply e to the minus 5/3, 1 plus 5/3 plus 5, 25 over 9. So this is Poisson distribution. Again, as I said, most of the time I will, but the hints and the examples that we give you an idea about when to use Poisson distribution. And as we will see, Poisson distribution is related also to the exponential distribution that we'll talk about in continuous time, because Boson talks about like customer arrivals, how many customers I would expect to be in the bank, but the time between them is also random, right? I do not have like into the bank each minute one customer arrives. No, customers are, the time between arrivals is also random, and that one it follows the exponential distribution. The distance between trees is random. The time between calls to a customer service is random. The distance between particles on a surface is also random. So as we will see, and some probability distributions, they are connected to each other, and whenever we have such a situation, we will talk about it in the class. Okay, so with this we are done with the discrete distributions. So I will post probably homework 2. Yeah, we extended homework 1. Some students asked to extend homework 1, so extended it till the end of the week. But we'll post homework 2 probably on Wednesday, which I will try not to have it long like homework 1. But I will ask at least one question on each distribution that we covered. And on Wednesday, inshallah, we'll start with the continuous distributions. Okay. One of you asked about the computer assignment. So in the remaining 3 minutes, let me turn on my camera, and probably I can show you. Okay, so this tells so in the computer assignment, you need to download an application called Wayne. I have this name in the handout that I posted to Blackboard. But Wayne is basically an application that was developed in Qatar in a research center that's owned by the university. I had the honor to co-found this research center. It's now a big center. When we started it, it had 3 people or 4 people. Now it has more than 60 people working in that center. And this center, they developed something like Google Map. I know most people, they use Google Map, but this application is gaining a lot of popularity in Qatar. It's a free application, of course, and it's customized for Qatar. So they have, I guess, more than 200,000 downloads so far. It's available for both Android and Apple. So you can find it in both stores. So you need to download it, and then you need to record some data in 7 days. So each day, I think I put what time, you go to the application and you just put Qatar University, or you need to set city center or Qatar University Center shopping mall. So I put here city center. Since I'm in the university, I cannot put university, so I put city center. And it gave me the shortest path is 10 minutes, 8.4 kilometers. So you record this in 7 consecutive days. In the morning, I put for the university. So assume that you will go to the university, so at 11 a.m. And then you take screenshot so that you include it in the report. And then in the evening, you see the time to get to the city center from your home. So you do this for 7 days, and you do you comment on the randomness of the data. I ask you in the report what you need to do. The second thing you need to do is where it is. 1 second. Okay. The application has other services. One of them is, sorry, let me go to the application. As you see at the bottom, it has many nice things, actually, many features that you don't find in Google Map. For example, if you can put the national address, it uses the national address in Qatar. You have the national address of one of the students. You can take you directly there. But I'm asking you to use the parking. It has a tab. It's called parking. You go to that parking, and each based on your ID. You just tell me. Can you turn off your mobile, your mics, please? In a certain time, just tell me the parking assigned to you, how many empty slots it has, and then you record that as well. So the whole purpose of the computer assignment is to, probably I should have assigned this earlier, again, to look into randomness of practical scenarios that we have around us, and also to introduce you to this application that it's homemade in Qatar, and probably you can start using it from now on. The research center is not a money generating entity. They will not gain if you use it, but again, this is designed and developed in Qatar, so it's a good chance for you to get exposed to it. So this is more or less, it should not take you, once you have the data, it should take you 1 hour just to develop the report and submit it for the class. Okay. So with that, I think I will stop the recording.